or no games in strategic form, chapter 2, 2.1. Game frames and games. Game theory deals with interactive situations where two or more individuals called players make decisions that jointly determine the final outcome. To see an example, point your browser to the following video at YouTube. In this video, each of the two players, Sarah and Steve, has to pick one of two balls. Inside one ball appears the word split, and inside the other, the word steal. Each player is first asked to secretly check which of the two balls in front of her or him is the split ball and which is the steal ball. They make their decisions simultaneously. The possible outcomes are shown in Figure 2.1, where each row is labeled with a possible choice for Sarah and each column with a possible choice for Stephen. Each cell in the table thus corresponds to a possible pair of choices and the resulting outcome, which is written inside the cell. We have a 2 by 2 grid, and on the horizontal side is split and still, and also on the vertical side is split and still. The top left quadrant yields split, where Sarah gets $50,000 and Stephen gets $50,000. The next quadrant over has a split on the horizontal axis and still on the vertical, and in this case Sarah gets nothing and Stephen gets $100,000. In the bottom left quadrant, Sarah on the horizontal side has steal and Stephen has split. And in this situation, Sarah gets $100,000, Stephen gets nothing. And in the fourth quadrant, the bottom right of the 2 by 2 grid is where Sarah steals on the horizontal axis and Stephen steals on the vertical axis. Sarah gets nothing and Stephen gets nothing. It's called Figure 2.1, the Golden Balls game. What should a rational player do in such a situation? It is tempting to reason as follows. Let us focus on Sarah's decision problem. She realizes that her decision alone is not sufficient to determine the outcome. She has no control over what Stephen will choose to do. However, she can envision two scenarios. One where Stephen chooses steal and the other where he chooses split. If Stephen decides to steal, then it does not matter what Sarah does, because she ends up with nothing no matter what she chooses. If Stephen picks split, then Sarah will get either $50,000 if she also picks split, or $100,000 if she picks steal. Thus, Sarah should choose steal. The above argument, however, is not valid because it is based on an implicit and unwarranted assumption about how Sarah ranks the outcomes. Namely, it assumes that Sarah is selfish and greedy, which may or may not be true. Let us denote the outcomes as follows. 01, Sarah gets $50,000 and Stephen gets $50,000. 02, or 02, Sarah gets nothing and Stephen gets $100,000. O3, Sarah gets $100,000 and Steven gets nothing. O4, Sarah gets nothing and Steven gets nothing. Table 2.1, names for the outcomes shown in figure 2.1. If indeed Sarah is selfish and greedy in the sense that in evaluating the outcomes, she focuses exclusively on what she herself gets and prefers more money to less, then her ranking of the outcomes is as follows. O3 is better than O1, which is better than O2, which is just as good as O4, which reads O3 is better than O1, O1 is better than O2, and O2 is just as good as O4. But there are other possibilities. For example, Sarah might be fair-minded and view the outcome where both get $50,000 as better than all the other outcomes. For instance, her ranking could be O1 is better than O3, which is better than O2, which is better than O4. According to this ranking, besides valuing fairness, she also displays benevolence towards Stephen, in the sense that when comparing the two outcomes where she gets nothing, namely O2 and O4, she prefers the one where at least Stephen goes home with some money. If in fact Sarah is fair-minded and benevolent, then the logic underlying the above argument would yield the opposite conclusion, namely that she should choose a split. Thus we cannot presume to know the answer to the question, what is the rational choice for Sarah? If we don't know what her preferences are, it is a common mistake, unfortunately, that even game theorists sometimes make to reason under the assumption that players are selfish and greedy. This is typically an unwarranted assumption. Research in experimental psychology, philosophy, and economics has amply demonstrated that many people are strongly motivated by considerations of fairness. Indeed, fairness seems to motivate not only humans, but also primates, as shown in the following video, a TED Talk. Do animals have morals? The situation illustrated in figure 2.1 is not a game, as we have no information about the preferences of the players. We use the expression game frame to refer to it. In the case where there are only two players and each player has a small number of possible choices, also called strategies, a game frame can be represented as we did in figure 2.1 by means of a table with as many rows as the number of possible strategies of player 1 and as many columns as the number of strategies of player 2. Each row is labeled with one strategy of player 1, and each column is with one strategy of player 2. Inside each cell of the table, which corresponds to a pair of strategies, one for player 1 and one for player 2, we write the corresponding outcome. Before presenting the definition of game frame, we remind the reader of what the Cartesian product of two or more sets is. Let capital S 1 and capital S sub 2 be two sets. Then the Cartesian product of capital S sub 1 and capital S sub 2, denoted by capital S sub 1 times capital S sub 2, is the set of ordered pairs. X1, comma x2, where x1 is an element of capital S sub 1, and x2 is an element of capital S2. X2 is the element of S2, capital S2. For example, if capital S sub 1 equals the set A, B, C, and capital S sub 2 is the set capital D, capital E, then capital S sub 1 times capital S sub 2 equals the set A, capital D, and A, capital E, and B, capital D, and B, capital E, and C, capital D, and C, capital E. The definition extends to the general case of capital of n sets, or n is greater than 2.